7.6 is improper integrals. So in these situations, we are looking at integrals that either have unbounded limits of integration, perhaps they might have infinite endpoints or even infinite integrands. So we need to investigate in different ways. So we'll take a look at a bunch of different types of examples for this section. So an improper integral by definition is we have a fixed number a, assuming that f of x is integrable from a to b, where b is greater than a, and the improper integral would be from a to infinity, is defined as the following. So if we have this integral, then we should be able to define the upper limit as r and take the limit as r approaches infinity. This will allow us to determine whether it converges or diverges. So this first example. So we can first rewrite the integral. From 2 to infinity of dx over x cubed, and that's equivalent to the limit as r approaches infinity of the integral 2 to infinity. 2 to r. dx over x cubed, which is just a reverse power rule. X cubed in the denominator is x to the negative third, so this would integrate to negative 1/2 x to the negative second from 2 to r. The integral is equal to this, which is then equal to negative 1/2 r to the negative second minus negative 1/2 2 to the negative second. Simplified is 1/8 minus 1 over 2r squared. So that's the integral portion. Now we take the limit as r approaches infinity. So the 1 over 2r squared portion would go to 0, and overall the limit converges to 1 over 8. This next one becomes first the limit as r approaches negative infinity of the integral r until negative 1. So if we integrate it, then we have the limit as r approaches negative infinity of ln absolute value x from r to negative 1. So we have the limit as r approaches negative infinity of ln 1 minus ln absolute value r, which ln 1 is just 0. So if we take the limit as r approaches negative infinity of negative ln of r, we're going to end up with negative infinity here. So therefore this diverges. So down here with theorem 1, the p integral from a to infinity for a is greater than 0 is given below. If p is greater than 1, you would have that result, and if p less than or equal to 1, then it will diverge. Here, this example 3, is using L'Hopital's rule, and you're also going to have to use integration by parts. So I'm going to write that up top. Just as a refresher, the integral of u of x v prime of x dx is equal to u of x v prime of x minus integral of u prime of x v of x dx. Sorry, backtracking. This is just v of x there. Okay. So first we can acknowledge that we can name x our u, and v prime is then e to the negative x. filling in everything else. So if we have 0 to infinity of x e to the negative x dx, this is equivalent to uv, so x, v would have been negative e to the negative x, so I'll put the negative out in front, plus the integral of u prime, which is 1, v. So it's e to the negative x. Right, and our sign changed here because it went from subtraction to addition because v is negative e to the negative x. So negative x e to the negative x minus e to the negative x plus a c for now, which is negative quantity x plus 1 e to the negative x plus c. Okay, so our last step, rather than having it from 0 to infinity, we can evaluate this integral from 0 to r and then take the limit as r approaches infinity. So negative quantity x plus 1 e to the negative x from 0 to r would yield negative quantity r plus 1 e to the negative r plus e to the 0. Or rewritten, 1 minus quantity r plus 1 over e to the r. And lastly, we will take the limit as r approaches infinity. So 1 minus the limit so here is where we can use L'Hopital's rule, right? Because as is, it's infinite over infinite, which is an indeterminate form in a fraction. If we derive the top, we would get 1. If we derive the bottom, we still have e to the r. So here's L'Hopital's rule. And now if I evaluate at infinity, I would have 1 over infinity, which would 0 out. So then I end up with 1 minus 0, or 1. Okay, so a little bit here. Take the time to read through this for sure. This is looking at infinite discontinuities, right? So if there is for example, some domain restriction where one of the limits is discontinuous, so it's not inclusive here on this integral, then we have to investigate our one-sided limit. So if the lower limit versus the upper limit is discontinuous, that would depend on whether we're looking at the left or the right. Okay, so I'm going to show you this example with part A and part B. So part A is the integral from 0 to 9 of dx over root x. So the root 0, the A, is what's not allowed. That would be a domain restriction. It would be a vertical asymptote there. Actually, in this case, it might not be an asymptote. I'm sorry, I have to look at the graph. But either way, it's a domain restriction. 0 is not allowed, but the domain is greater than 0. So anyways, we are going to look at 0 on the right-hand side because that's where the graph is defined. So we're going to look at the limit as r approaches 0 from the right, r to 9, x to the negative 1/2 dx, which would integrate to 2x to the positive 1/2. We still have to evaluate from r to 9. So finally, we'll be taking the limit as x approaches 0 on the right. We would have the square root of 9 is 3 times 2 is 6, plus 2 root r. I'm sorry, minus 2 root r. Okay. And if we evaluate this at 0, we would just end up with 6. Okay. So example B, we have the integral from 0 to 1/2 dx over x. So we're going to do the same thing here. 0 is not allowed, but in this case, we do have, for sure, an asymptote at 0. But because 1/2 is on the right, we're still going to look at the right-hand side of 0. So this is going to end up with ln from r to a half. Okay, so we have ln of a half minus ln of r. And if we evaluate the limit at 0, if you just visualize what the graph of the natural log is and what is happening at 0 is where that asymptote is, and the graph is approaching negative infinity at 0. So therefore, this is really ln of 1/2. It's approaching negative infinity, I'm sorry, so minus a negative infinity. So it goes to positive infinity. Okay. So theorem 2 now, the p integral over 0 to a versus the 0 to infinity. Similar idea, but not the same result, so use caution here. So if p is less than 1 now, we have that result. If p is greater than 1, it diverges. So let's take a look at this example, remembering that the integral of dx over square root 1 minus x squared is equal to sine inverse. Let's see. So this integral is equivalent to the limit as r approaches 1 from the left, right, because 1 is what would not be allowed in this. The integral 0 to r okay. So then this ends up integrating first to sine inverse of x from 0 to r. So we'll have sine inverse of r minus sine inverse of 0. And if we evaluate this limit at 1, sine inverse of 1 minus sine inverse of 0 ends up being pi over 2 minus 0, or pi over 2. Okay, comparison test for improper integrals. So if you can prove that a function is larger than another function, and that said function converges, then the other one also converges. And then if it's in the reverse direction, if the smaller one diverges, then so does the larger one. Okay, so you have to be careful of which direction you're sort of proving it in and what solution you end up getting. So it's a little bit of a guessing game and making sure that you pick the right one. And if you don't, then you have to go back to it. So we can't evaluate the integral as is, so we're going to compare with a larger function. So we can use x to the negative 3/2, or because, first of all, x cubed and the square root is going to be less than the x cubed plus 1, right? And therefore, if I actually compare to the function at hand and put it under 1, then the opposite is true. And that's what we were looking for, okay? So if we can prove that the x to the negative 3/2 converges, then we can say the same thing would be true for the 1 over x cubed plus 1. So if we use our p integral, we see that p is greater than 1, right? 3/2 is greater than 1. Therefore, this converges. Look back at the table just to confirm that. So if the f, which is the larger function here, converges, then the g will also converge, is what we're going off of. Okay, we have 2 more examples that I'm going to do from the textbook in this note set. So the next one, looking at does the integral from 1 to infinity dx over root x plus e to the 3x, does this converge? So first it's important to acknowledge that root x is positive, right? So therefore root x plus e to the 3x is going to be at least larger than or equal to e to the 3x. And then if we flipped it, the opposite would be true, right? 1 over root x plus e to the 3x is less than or equal to 1 over e to the 3x. So working with this, integral 1 to infinity of dx over e to the 3x, it's equivalent to the limit as r approaches infinity of negative 1/3, right? Remember, e to the 3x in the denominator is e to the negative 3x, so I'm dividing by negative 3 when I'm anti-deriving it. E to the negative 3x from 1 to r, which is then equal to the limit as r approaches infinity of negative 1/3 e to the negative 3r plus 1/3 e to the negative 3. And if I evaluate this at infinity, because it's a negative exponent, that drops to the denominator, so we have number over infinity, which this term then zeroes out, so we're left with 1/3 e to the negative 3rd, which numerically is not relevant, but the fact that it converges is. So therefore we can conclude, because this other function is smaller, based on that table, the comparison table, then this original function also converges. Okay, this last example ends up going in the other direction. So let's take a look at this. So does j equal integral 0 to 0.5 dx over x to the 8th plus x squared? Does it converge or does it end up diverging? So similar logic, right? X to the 8th plus x squared, that's going to be greater than x squared. Okay. And therefore, 1 over x to the 8th plus x squared is less than 1 over x squared. Okay, but from 0 to 0.5, dx over x squared diverges based on the table. So therefore, just writing this out, this is not helpful because we need a smaller f of x, or smaller function, if it's divergent. So back to the drawing boards. So then if we think more closely, well, we're looking between 0 and a half. So then therefore, x to the 8th in that domain is less than x squared, right? X to the 1/4, for example, is going to be less than the x squared, x to the 8th versus x squared. So then therefore, x to the 8th plus x squared would be less than 2x squareds. And the opposite, 1 over x to the 8th plus x squared is greater than 1 over 2x squared. So from 0 to 0.5 of dx over 2x squared, this diverges based on the table, and therefore j also diverges. Okay, so that is the last section in chapter 7.